NENOMATICA, where mathematics meets YouTube excellence. In this video, we will prove that the quadratic equation open parenthesis m minus 1 close parenthesis x squared minus 3m x plus 1 minus m equals 0 has two distinct real roots for all real values of the parameter m where the equation is truly quadratic. We will do this by showing that its discriminant is strictly greater than 0. First, identify the coefficients. Here, at equals m minus 1, b equals negative 3m, and c equals 1 minus m. Note, to truly have a quadratic, we require a not equal to 0, so m not equal to 1. For m equals 1, the equation becomes linear, not quadratic. The condition for two distinct real roots is discriminant greater than 0. That is, delta equals b squared minus 4. AC is strictly greater than 0. Substitute a, b, and c. Delta equals negative 3m squared minus 4 times open parenthesis m minus 1 close parenthesis times open parenthesis 1 minus m close parenthesis. Recognize that 1 minus m equals negative of m minus 1. So delta simplifies to 9m squared plus 4 times m minus 1 squared. This is a sum of two non-negative terms. Now, 9m squared is at least 0, and 4 times m minus 1 squared is at least 0. Equality to 0 would require m equals 0 and m equals 1 simultaneously, which is impossible. Therefore, delta is strictly greater than 0 for every real m. So whenever the equation is truly quadratic, that is, when m is not equal to 1, the discriminant is positive, and the quadratic has two distinct real roots. At m equals 1, the equation reduces to negative 3x equals 0, which has a single real root at x equals 0, not two distinct roots. As an alternative confirmation, expand 4 times m minus 1 squared and combine with 9m squared. This gives 13m squared minus 8m plus 4. Its discriminant is negative 8 squared minus 4 times 13 times 4, which equals 64 minus 208 equals negative 144, less than 0. With leading coefficient positive, this quadratic in m is always positive, matching our sum of squares argument. Final conclusion. For all real m not equal to 1, the equation is quadratic and has two distinct real roots because the discriminant is strictly positive. At m equals 1, the equation is linear and has one real root x equals 0. Example, if a, b, and c are sides of a triangle, prove that the quadratic expression a of x, which equals b squared x squared plus the quantity b squared plus c squared minus a squared times x plus c squared, is always positive for all real x. Our strategy will use a classic test for quadratics to be always positive. A quadratic ax squared plus bx plus c is always positive for all real x if the leading coefficient a is positive, and the discriminant delta is negative. In our expression, the leading coefficient a equals b squared, the middle coefficient b equals b squared plus c squared minus a squared, and the constant c equals c squared. Step 1. The leading coefficient a equals b squared. Because b is a side length of a triangle, b is positive, so b squared is positive. This satisfies the first condition. To prepare for the discriminant part, let's visualize a triangle with sides labeled a, b, and c. We'll use the triangle inequality soon. Each pair of sides adds to more than the third. Step 2. We show the discriminant is negative. The discriminant equals b squared minus 4ac. Substituting our values, delta equals the quantity b squared plus c squared minus a squared, all squared, minus 4b squared c squared. This is a difference of squares. Let x equal b squared plus c squared minus a squared, and let y equal 2bc. Then delta equals x minus y times x plus y. Step 3. Regroup inside each bracket as perfect square trinomials. b squared minus 2bc plus c squared equals the quantity b minus c squared. b squared plus 2bc plus c squared equals the quantity b plus c squared. Therefore, delta equals the product of the quantity b minus c squared minus a squared, and the quantity b plus c squared minus a squared. Step 4. Apply the difference of squares once more. For each factor, x squared minus a squared equals x minus a times x plus a. Thus, Delta equals the product of four linear terms, b plus c plus a times b plus c minus a times b minus c plus a times b minus c minus a. Step 5. Use the triangle inequalities to sign each factor. We reintroduce the triangle diagram and list the true inequalities. The sum b plus c plus a is positive. The difference b plus c minus a is positive because b plus c is greater than a. The expression b minus c plus a is positive because a plus b is greater than c. The last factor b minus c minus a is negative because a plus c is greater than b. Therefore, the product is negative. So delta is less than 0. Final step. We have a greater than 0 and delta less than 0. Therefore, the quadratic b squared x squared plus the quantity b squared plus c squared minus a squared times x plus c squared has no real roots and opens upward. So a of x is strictly positive for every real x. Recap. We use two facts. 1. The leading coefficient b squared is positive because b is a side length. 2. The discriminant simplifies, via difference of squares twice, to a product of four linear factors whose signs are determined by the triangle inequalities. The product is negative, so delta is negative. Hence the quadratic is always positive. In this example, we will find all real values of m such that the quadratic expression 4x squared minus 2mx plus 4m squared is greater than or equal to 0 for all real x. A quadratic ax squared plus bx plus c is always non-negative for all real x if and only if two conditions hold. 1. The leading coefficient is strictly positive, and 2. The discriminant is less than or equal to 0. Because b is an even coefficient here, we will use the simplified discriminant delta prime equals b prime squared minus ac, where b prime is b over 2. In our expression, at equals 4, b equals negative 2m, and c equals 4m squared. Therefore, b prime equals b divided by 2, which is negative m. Now, apply the condition delta prime less than or equal to 0. We substitute b prime squared minus ac less than or equal to 0. That is negative m squared minus 4 times 4m squared less than or equal to 0, which simplifies to m squared minus 16m squared less than or equal to 0. Combine like terms to get negative 15m squared less than or equal to 0. Dividing both sides by negative 15 flips the inequality, so m squared is greater than or equal to 0. Since m squared is always non-negative for any real m, we conclude that all real m satisfy the original inequality for all x. For extra intuition, we can complete the square in x. Start by grouping the x terms. 4 times x squared minus 1/2 m times x plus 4m squared. Inside the brackets, x squared minus m over 2 times x becomes x minus m over 4 squared minus m squared over 16. So the entire expression equals 4 times the square of x minus m over 4 plus 15 over 16m squared, all multiplied by 4 outside. That simplifies to 4 times the square of x minus m over 4 plus 15/4 m squared. This is clearly always non-negative, and it equals 0 only when m equals 0 and x equals 0. Let us visualize the parabola for different values of m to see why this is always non-negative. We plot y equals 4x squared minus 2mx plus 4m squared on the same axis. As we vary m, notice the graph remains above or touches the x-axis and never dips below. The minimum value occurs at x equals m over 4 and is equal to 15/4 m squared, which is always non-negative. Example, if a, b, and c are real numbers, prove that the quadratic equation open parenthesis x minus a close parenthesis times open parenthesis x minus b close parenthesis plus open parenthesis x minus b close parenthesis times open parenthesis x minus c close parenthesis plus open parenthesis x minus c close parenthesis times open parenthesis x minus a close parenthesis equals 0. Always has real roots. Step 1. Expand and simplify. We expand each product using x minus p times x minus q equals x squared minus the sum p plus q times x plus pq. First term expands to x squared minus open parenthesis, a plus b close parenthesis x plus ab. Second term expands to x squared minus open parenthesis, b plus c close parenthesis x plus bc. Third term expands to x squared minus open parenthesis c plus a close parenthesis x plus ca. Step 2. Combine like terms to get a standard quadratic in x. Adding all three expansions gives 3x squared minus the quantity 2 times a plus 2 times b plus 2 times c, all times x plus ab plus bc plus ca. That is 3x squared minus 2 times open parenthesis, a plus b plus c close parenthesis times x plus open parenthesis, ab plus bc plus c a close parenthesis equals 0. So we can identify a equals 3, b equals negative 2 times open parenthesis, a plus b plus c close parenthesis, and c equals ab plus bc plus c a. Step 3. Condition for real roots. A quadratic ax squared plus bx plus c equals 0 has real roots when its discriminant is non-negative. Because b is even, we use the reduced discriminant delta prime equals b over 2 squared minus ac. Here, b over 2 equals negative of a plus b plus c. So delta prime equals open parenthesis, a plus b plus c close parenthesis squared minus 3 times open parenthesis, ab plus bc plus c a close parenthesis. Step 4. Simplify delta prime. Expand a plus b plus c squared as a squared plus b squared plus c squared plus 2 times open parenthesis, ab plus ac plus bc close parenthesis. Then delta prime becomes 4 times open parenthesis, a squared plus b squared plus c squared close parenthesis, minus 4 times open parenthesis, ab plus bc plus c a close parenthesis, all divided by 1, which we write as 4 times the quantity a squared plus b squared plus c squared minus b minus bc minus ca. Step 5. Show non-negativity. Use the identity twice times open parenthesis, a squared plus b squared plus c squared minus b minus bc minus c. A close parenthesis equals open parenthesis, a minus b close parenthesis squared plus open parenthesis, b minus c close parenthesis squared plus open parenthesis, c minus a close parenthesis squared. Since every square of a real number is non-negative, their sum is non-negative. Therefore, the expression a squared plus b squared plus c squared minus ab minus bc minus c is greater than or equal to 0. Hence, delta prime is greater than or equal to 0, and the equation always has real roots. Example, we will prove that the equation open parenthesis x minus 1 close parenthesis times open parenthesis x minus 3 close parenthesis plus m times open parenthesis x minus 2 close parenthesis times open parenthesis x minus 4 close parenthesis equals 0 has 2 real roots for every value of m, and we will also carefully check the special case when the quadratic coefficient could be 0. Step 1. Expand each product. The first product becomes x squared minus 4x plus 3. The second product becomes x squared minus 6x plus 8, multiplied by m. Step 2. Distribute m, combine like terms, and write the standard quadratic form ax squared plus bx plus c equals 0. Here, a equals m plus 1, b equals negative of 6m plus 4, and c equals 3 plus 8m. Step 3. Apply the discriminant condition for 2 real roots. Delta equals b squared minus 4, ac must be greater than or equal to 0. Substitute a, b, and c. Step 4. Now simplify. The square of 6m plus 4 is 36m squared plus 48m plus 16. The product 4 times open parenthesis m plus 1 close parenthesis times open parenthesis 3 plus 8m close parenthesis simplifies to 4 times 8m squared plus 11m plus 3. Subtract and combine like terms to get 4m squared plus 4m plus 4, which equals 4 times open parenthesis m squared plus m plus 1 close parenthesis. Step 5. Show that m squared plus m plus 1 is always positive. Complete the square. M squared plus m plus 1 equals open parenthesis m plus 1/2 close parenthesis squared plus 3/4, which is strictly greater than 0 for every real m. Step 6. Since m squared plus m plus 1 is always positive, the discriminant equals 4 times that, which is strictly positive for all m. That guarantees 2 distinct real roots whenever the quadratic coefficient equals m plus 1 is not 0. There is one subtle special case. When m equals negative 1, the coefficient becomes 0. In that case, the equation is not quadratic. It simplifies to a linear equation 2x minus 5 equals 0, whose single real solution is x equals 5/2. Therefore, for all m not equal to negative 1, there are two distinct real roots, and at m equals -1, there is one real root from the linear equation. Final summary. For all m not equal to -1, the equation is a genuine quadratic with positive discriminant, hence two distinct real roots. For m equals -1, it becomes linear with one real root equal to 5/2. Therefore, the original equation has real solutions for every real m, and has two real roots for all m except -1. In this example, we will prove that the roots of the equation at times open parenthesis x squared minus 1 close parenthesis equals x times open parenthesis b minus c close parenthesis are always real numbers. First, let's show the problem clearly on screen. Step 1. Rearrange the equation into the standard quadratic form, ax squared plus bx plus c equals 0. We begin with a times open parenthesis x squared minus 1 close parenthesis equals x times open parenthesis b minus c close parenthesis. Apply the distributive property on the left. Ax squared minus equals x times open parenthesis b minus c close parenthesis. Now move everything to one side. Ax squared minus open parenthesis b minus c close parenthesis x minus a equals 0. This is the standard form. Step 2. Identify the coefficients and write the discriminant condition for real roots. Here a equals a, b equals negative open parenthesis, b minus c close parenthesis, and c equals negative a. For a quadratic to have real roots, its discriminant delta must be greater than or equal to 0. That is b squared minus 4, ac is greater than or equal to 0. Step 3. Substitute a, b, and c into the discriminant and simplify. Substituting gives bracket negative open parenthesis b minus c close parenthesis bracket squared minus 4 times a times negative a greater than or equal to 0. That simplifies to open parenthesis b minus c close parenthesis squared plus 4 squared, which is greater than or equal to 0. Step 4. Build intuition with a visual. The expression is the sum of two squares. A square like open parenthesis b minus c close parenthesis squared can never be negative, and 4 squared can never be negative. Therefore, the sum is always non-negative, so the discriminant is at least 0, guaranteeing real roots. One quick edge case. If it equals 0, then the left side is 0, and we get x times open parenthesis b minus c close parenthesis equals 0. If b is not equal to c, then x equals 0 is a real solution. If b equals c, every real x satisfies the equation. In all cases, solutions are real. Therefore, the discriminant is always non-negative, and the equation has real roots for all real a, b, and c. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.